Welcome everybody. Today is the first class of the course Geometry of Numbers. During the whole course, we'll see something regarding the relations between numbers and geometry. And first of all, let's look at something that everybody is feeling familiar with. So you see now you're given a right angle triangle. I give the length of the base length as A and the vertical length as B, and the hypotenuse, which is the longest length of this right angle triangle, to be C. There's a very famous relation between ABC. Can you recall that? I believe you have seen it in high school anyway. And the relation is that the lengths ABC are governed by the relation here, A squared plus B squared equals C squared, and people normally call it Pythagoras Theorem. And then the next one. Can you give me some examples, ABC, so that they are governed by this relation? I believe that you can give me some examples pretty quickly. For example, like this one. A equals 3, B equals 4, and C equals 5. So in that case, you'll get the following. That they are actually exactly governed by this relation, Pythagoras theorem, that 3 squared plus 4 squared equals 5 squared. And then the next one. We can look at this possibility that A equals 8, B equals 15, and C equals 17. In that case, you can easily verify the following. That 8 squared plus 15 squared equals 17 squared. So it's the other example for ABC, so that they will give exactly the length for a right angle triangle. So now let's give it a name. Whenever the three values of ABC, they are governed by such a relation of Pythagoras theorem, we'll give it a name and call it Pythagoras triple. So we have already seen two examples. The first one is 3, 4, 5. The second one is 8, 15, and 17, respectively. So let me give a third one now. And can you tell me some similarity of the third one and the first one? So the third one, I claim 6, 8, 10 is also another Pythagoras triple. Why is it like that? Because you can easily verify that 6 squared plus 8 squared is actually equal to 10 squared. You can check it yourself. And back to my original question, I'm asking, is there any common similarity, common property between the first one, 3, 4, 5, and the third one, 6, 8, 10? I believe you can tell me that the common property is that because of the fact that there's a common multiple of 2 among the three numbers 6, 8, 10. If you divide the 2 as a factor out of the three numbers 6, 8, 10, you can easily get back to the original triple 3, 4, 5 in the first example, right? So now, geometrically speaking, for these two sets of triples, you can obviously construct a right angle triangle whose lengths are exactly the Pythagoras triple in the first example and the third example. And again, in terms of geometry of the right angle triangle, they are very similar because these two triangles are actually similar, which basically means that geometrically speaking, they give you two triangles. They are quite similar in terms of the geometric properties, and in our course we normally don't like to consider things that are similar in terms of the geometric properties. So regarding this, from now on, whenever the Pythagoras triple has a common multiple bigger than 1, just like the third example which has a common multiple 2, we try to avoid talking about those triples because they are not really giving us anything essentially different. So because of this, we have to give it a name for all the Pythagoras triple which doesn't have a common multiple bigger than 1, and in that case we call it primitive Pythagoras triple. When there's no confusion that possibly occur, we just simplify to call it primitive triple in most of the cases during the course. And again, let me repeat the meaning of such a definition. It basically means that the triple of three numbers ABC, they don't have any common multiple bigger than 1. That's what I meant by primitive triple. And obviously for those cases that the three numbers have common multiple bigger than 1, I just call it imprimitive triple. And in this course we mostly follow the definition primitive triple, we focus on that. And now, there's a very interesting question for all of you to look at. The question is here, is there any systematical method to construct ABC? In the previous three examples we looked at, They are more like trial and error to all of us. So up to now, we don't really know is there any good way, systematic way, computational way to construct such a primitive triple ABC. And that's actually the core question during the course. We'll try to answer this problem first during the first couple of lectures. So this video is really just the introduction during the course. And if you're interested in this question and anything like geometry and algebra surrounding the Pythagoras theorem, please follow this channel. And now that's the end of this video. Thank you everybody.